Hello
Hello
everyone.
everyone.
I'm recording this video because uh, we cannot have in-person lecture on coming Thursday because of my business trip. So, okay, please watch this video before the next class. Okay. So what did we learn in the previous class? We learned how to implement a pipeline process architecture. So this is the start point. Okay. So from the single cycle process architecture, we can split. We can split a data path element and then the data path between these hardware component like data path element. Okay, so we already learned that the pipeline architecture is composed of 5 stages. Okay, so this is because when an instruction is executed, and this instruction execution is also composed of 5 steps. What are 5 steps? Instruction fetch, instruction decoding, execution and memory, and write back, right? So I explained that we can insert pipeline registers between pipeline stages. Okay, so as I mentioned, the pipeline registers are groups of D flip-flops, right? So these are different from the normal or general purpose registers in RISC-V instructions. Okay. So these are just D flip-flops, okay, and then synchronized by clock signal. Okay, and then actually I use the load instruction to explain the behavior of this pipeline architecture, right? So load instruction can be fetched and then decoded. This is the instruction decoding stage, and then so actually for load instruction we need to compute addresses, right? So addresses in the ALU, and then the load instruction accesses data memory, then the result. The result is written back. So I mentioned that we need to consider the timing of data, and then also the timing of register number, the destination register number, right? So I mentioned that this part is wrong. Why? Because the result of load instruction is written back in the write back stage. So actually this data is written back to the register file. And so in this case, we need to use the RD of load instruction, right? And then, but if you see this RD, this write register, the write register is in the ID stage. And then, so in the pipeline architecture, there are different instructions in the different stages, right? So it means the load instruction is in the write back stage. So the instruction in the ID stage is the different instruction. So RD, this RD is the RD of different instruction, not the load instruction in the write back stage. So in order to resolve this incorrect connection, we need to provide the RD in write back stage, right? So you can find that the RD, this is the write register. So this is the RD. So RD is propagated to the pipeline registers, right? So this is the RD in ID stage. What is this RD? So this is the RD in EX stage. This is the RD in memory stage. And then this is the RD in write back stage. So the data in write back stage is written back to the register file. So we need to use the RD in write back stage. So I mentioned that this is very critical. So we need to align the timing of data in the pipeline architecture, right? Okay. So and then I will explain about the another example, the store instruction. So store instruction compute the target address using ALU. So this is the store instruction in EX stage. Then store instruction also accesses data memory using the address and write data. And then the store instruction is completed in the memory stage. But in the pipeline architecture, all instructions need to go through the all stages in this pipeline architecture. So even though actually we don't need to write back the result. Actually, there is no result in the store instruction. But so we don't need to write back the store instruction. But as you can see, the store instruction is also in the write back stage. But this store instruction does nothing. Okay, because the store instruction does not write the result to the register file, right? So, but as I mentioned, every instruction needs to go through the all stages in the pipeline architecture. Okay, so we can represent the how instructions are executed in the pipeline architecture. So in this example, so in this figure, you can find the time. So we can represent the time of this pipeline architecture using the clock cycles. So it is because the the CPUs are also digital systems, and I mentioned that all digital systems work with clock signals. So and then actually each instruction performs its required steps in the individual pipeline stage within one clock period. So we can represent the time as a clock cycle, like the CC1, CC2, CC3, blah, blah, blah. So it means the clock cycle. Also, this vertical axis, vertical position represent the instructions. And then, so instructions are executed sequentially from top to bottom, right? So this vertical position represents the instruction stream, right? And then instruction, as you can see, instructions are executed from top to bottom. So the first instruction is load instruction. So in a clock cycle 1, the load instruction is in the instruction fetch stage, right? And then in a clock cycle 2, the load instruction is propagated to the ID stage. And then at the same time, in the same clock cycle, then sub instruction. The next instruction is fetched. So sub instruction is in the instruction fetch stage. And then in clock cycle 3, the load instruction in the ID stage is propagated to the EX stage, right? And then the sub instruction is in the ID stage. And then the next instruction, the add instruction is in the instruction fetch stage. So as you can see, at every clock, instructions are fetched. And if there is no hazard, then instructions can be propagated to the next pipeline stage every cycle, right? So let's see the clock cycle 5. So if you see the clock cycle 5, so you can find that the load instruction is in the write back stage, and then sub instruction is in the memory stage. This is the write back, and then add instruction is in the EX stage, and then another load instruction is in the ID, and then another add instruction is in the instruction fetch stage. So if we just focus on this clock cycle, the clock cycle number 5, then we can observe that multiple instructions. Okay, actually, we can observe 5 different instructions in the 5 different pipeline stages. So, we can say that with the pipelining architecture, the instructions, multiple instructions are being executed in parallel. Okay, and then this is called the instruction level parallelism. And then it is called the ILP, instruction level parallelism. So instruction level parallelism means multiple instructions. Multiple instructions can be executed, processors in parallel. Okay. So the pipeline architecture exploit the instruction level parallelism to increase the performance of the CPU. Okay. So, and it is because at the same time, we can observe multiple instructions in the different pipeline stages. Okay. Okay, so we can represent the same pipeline operations in the different form. Okay, so like the rectangles. Okay, and then we can also represent some different instructions in the different pipeline stages. So if you see this figure, then you can find that the load instruction is in the write back memory, the sub instruction is in the memory stage, and then add instruction is in the execution. Then another load instruction is in the ID stage, and then another add instruction in the instruction fetch stage. So you can figure out that this is the CC5 time. Okay, well, we can observe the multiple instructions. So we can observe different instructions are in the different pipeline stages. Okay. Also, so one student asked questions. So why we need to use this RD? So if you see this load instruction, this RD, so this is the RD in write back stage, right? This is the RD in write back stage. So what is this RD? This RD is the X10, right? But So you can find the different load instruction in the instruction decode stage. So what is this RD in ID stage? So this RD is the RD of this load instruction. So this is the X13. So it's different. So actually, so in the write back stage, this load instruction, this load instruction is writing data to the register file using this RD, right? So that's why we need to propagate the RD to the write back stage. Okay. Okay, so the database is okay. Okay, so I explained about the database design in the pipeline architecture. Then how about the control signals? In the single cycle processor design, we also implement the control signals. So firstly, we implement the control unit, then control unit generate the control signals based on the instructions, right? And then these control signals are connected to the control signal port in the data path element, right? So do you remember? Then how about the pipeline architecture? So we can just connect the control signals from the control unit to this control signal port in the single cycle processor design, right? But how about the pipeline architecture? So as you can see, so we can use the same data path element in the pipeline architecture, right? So this is the same instruction memory, and this is the same register file, the same ALU, same data memory. So data path element is the same. So which means this database element also includes the control port. Also the AL source is here, AL OP is here, mem read is here. Next question. How can connect the control signal to the control port? So you need to remember that we need to use control signals when required. So what does that mean? When the control signals are used. What does that mean? So think about this. So for example, let's think about the reg write. When is this reg write required? Do you understand? So when is this reg write is used or required? When the instruction is in the write back stage. So actually we use reg write signal for write back operation on an instruction. So I mentioned when the instruction is in the write back stage. So which means this reg-write signal is required in when the target instruction is in the write back stage. Then how can we generate this reg-write signal? Okay, but you need to remember this rule. Okay, let's see. So when the instruction is if we fetch instruction from the so in the single cycle process design, when an instruction is fetched from the instruction memory, then this instruction is given to the control unit, right? And then control unit can generate the control signals, right? Okay. So many control signals, but some control signals are used in the EX stage, or some control signals are used in the memory stage, and then some control signals are used in the write back stage. Okay, so that's what I explained. This regulator signal is used when an instruction is in the write back stage. It means if the regulator signal is used in the write back stage, then we need to propagate this regulator signal into the write back stage. So it's similar to the RD and data of load instruction, right? So actually, the data is written back to the register file when an instruction is in the write back stage. So I mentioned that we need to align the timing of data and this RD, right? So we use the RD in write back stage because this RD is used when an instruction is in the write back stage, right? So it's the same. It's the same. I mentioned, read write is used when an instruction is in the write back stage. So which means we need to use the read write signal in write back stage. Do you understand? Okay, so we did, because the reg write is used when an instruction is in the write back stage. Okay, so we need to use the reg write in write back stage. So reg write needs to be propagated to the write back stage. This is the rule. Okay, so also the control signals needs to be aligned. The timing of control signal needs to be aligned. Okay, let's see how the control signals are connected. So let's see the reg-write signal. So instruction is fetched from the instruction memory, right? And then this instruction is propagated to the ID stage, right? So this is the instruction. So the instruction in ID stage. So instruction is given to the control unit, and then control unit will generate the control signals. And then these signals are in these are control signals in ID stage, right? So you can find that these control signals are propagated to the next stage. What is the next stage? Next stage is the EX stage. So control signals are propagated to the EX stage. So these control signals, this one, these are control signals in EX stage, right? So you can find the ALU source. ALU source here, right? Also, you can find the Oops. ALOP signal here. So if you see the ALU source and then ALOP, then you can find that. So this processor used the ALU source in EX stage, right? And so ALOP is connected to the ALU control signal in EX stage. So why? Because we use ALU source when the instruction is in the EX stage. So its control signal is also connected to this multiplexer with the ALU source in EX stage. Also, this multiplexer is in the EX stage. So as I mentioned, the ALU source is used when an instruction is EX stage. So we use the ALU source in EX stage. And then ALUOP is the same. The ALUOP is used when an instruction is in the EX stage. Right. So you can find the AL control is also in the EX stage. So in this case, we need to use the ALOP signal in EX stage. Then, how about the mem write? And so you can find the mem read. So these are memory control signals, right? And then we use these mem write and mem read signals in memory stage. So that's why you can find this is the control signals in EX stage, and then it is also propagated to the memory stage. Okay, using via EX mem pipeline register. So this is the control signals. This is the control signals in memory stage. Okay, so the mem write is in the memory stage, so we use the mem write in memory stage. Also, mem read in memory stage. Also, the branch instruction. The branch instruction used the result of ALU, right? You can find the 0 here, but 0 is also propagated to the memory stage. Also, then this 0 signal is ended with the branch. So this AND gate is in the memory stage. So which means this branch signal, the branch control signal, is also used in the memory stage. So we use the branch in memory. So timing is online. This is okay. The timing of a control signal, and then the timing of a control signal is aligned with the instruction in the pipeline architecture, right? So how about the mem to reg? So you can find that this multiplexer is in the right backstage, right? So we use the mem to reg signal in right backstage. So you can find that this is the control signal in the memory stage, and then this is the control signal in the right backstage, right? So the mem to reg is given to this multiplexer, but we need to use the mem to reg in right backstage. Also, reg write. So you can find that the reg write is connected to, so it's connected from this signal, the control signal. So this control signal in right backstage, because as I mentioned, the reg write is used when an instruction is in the write back stage, right? So, okay, so I explained how the control signals are connected, right? So you can, I believe you can understand the timing of these control signals, right? Okay, now so let's see how the pipeline architecture can handle data hazard. Okay, so let's see this example. So in this example, you can find the instruction stream here, and then there are 5 instructions. And then sub instruction has the X2 as RD, the destination register. So which means the sub instruction stores the result in the X2. And then as you can see, 4 following instructions and or add store instructions receive X2, which means the result of sub instruction. Okay, so this is the the very dramatical the data dependencies. So X2 is generated by sub instruction, and then this X2 is consumed by the following instructions. So here, 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 and here. So we can observe our data dependencies in this example, right? And then, so using data forwarding, that we can avoid the data hazard, right? Then how? So let's see the data forwarding in the pipeline diagram. So as you can see, this the x-axis. X-axis represent the time, is a clock cycles. Then the y-axis represent the instruction stream, right? And then the sub instruction stores the data to the x2. When on sub instruction is in the write back stage. So we can observe that the x2 will be finally return back to the register file when an sub instruction is in the write back stage, right? But and then the following instructions, so it's the write back stage. The following instruction requires the data from this sub instruction, and then we already learned that using data forwarding, then this data, the result of ALU provided can be provided to the next instructions, right? The how. So this is the very next instruction, end instruction, and then it requires the x2, right? So actually, as I explained in the previous class, so x2 is generated by this ALU. So actually the processor can have the x2 data, the data from the sub instruction, the result of sub instruction at this point. And in order to perform the AND operation, so you know the AND operation is performed by ALU. So which means actually for this AND instruction, we require data at this point. So data can be forwarded. So what is this data? And then so So as you can see, this data can be forwarded. Okay, so this is the data forwarding from the output of ALU to the input of this ALU, right? So, but actually, so the data is required at this point, and then this X2 data. X2 data is also propagated to the memory stage. Okay, so and then this is the X2, the result of ALU by this pipeline register. So this is the EX and memory pipeline register. So we can use the X2 value, the generated by this EX and then memory pipeline register. So this can be forwarded to this ALU, right? Then how about the OR? It also requires X2 data. So in this case, so actually the OR requires X2 data at this point, right? And then where is this X2 data? X2 data is in this one. So this is the output by memory and write back pipeline register. So because the X2 needs to be written back to the register file, right? So which means this result needs to be propagated to the write back stage, right? So the memory and write back pipeline register also have the X2. So this X2 can be forwarded, right? Then how about this add? So in this example, the add needs to fetch the data from the register file, right? But at the same time, in the same cycle, this X2 is being written back to the register file, right? So in this clock cycle 5, so X2 is being written, and then also X2 is read by this add instruction, right? So in the same cycle, so actually this forwarding is performed by register file. So which means, so in the same cycle, the X2 is being written, and then the same X2 is read by add. So, and then this can be forwarded inside of the register file. Okay. So add instruction can read this data, the X2, because the register file can support internal forwarding. So this is called the internal forwarding. So which means that, so when the register write or register read is performed in the same cycle, then this data can be forwarded to the read out port of the register file. So this is the internal forwarding. So the add instruction also requires the data, and then but this data is being written by this sub instruction when a sub instruction is in the write back stage, but the register file support the internal forwarding, so this data can be read in the register file. How about the store instruction? So store instruction requests the register operands in the clock cycle 6. And then we can observe that actually the result x2 is already written back. Okay, so which means we can find this x2 data in the register file. Okay, so we require actually when we observe data dependency between the former instruction and the following instructions, then we need to support the data forwarding for the next 3 instructions. Okay, so and then but these 2 instructions like AND instruction and OR instruction, then the processor needs to support the forwarding, data forwarding. Okay, and then this add instruction, this add instruction, the forwarding is internally performed in the register file, so it can be supported by internal forwarding in register file. Okay, so for the pipeline architecture design, we need to consider this case. Okay, so then how can we implement the data forwarding logic? So how can you check the data forwarding? In this example, we can just check the RD of the former instruction and RS1 or RS2. These are source registers of the following instructions. So for example, for end and sub, we can check the RD of the sub instruction, and then we can check the RS1 and RS2 of the end instruction. And then in this example, the RD of the sub instruction is equivalent to the RS1 of the end instruction. So we need to perform data forwarding. So how about the sub and OR instruction? So we need to also check the RS1 and RS2, right? And then the RD. If the RD is equivalent to the RS1 or RS2 of OR instruction, then we can perform data forwarding. And when the forwarding is performed, target instruction is in the EX stage, right? And so also the forwarding is performed for this OR instruction when the OR instruction is in the EX stage. So what does that mean? We can check the RS1 or RS2 in EX stage and RD in the different stage, like the memory stage or write back stage. Okay, so as I mentioned, we can just check the RD and then RS of the former and following instructions, right? But we need to check the data forwarding condition when the target instruction means that target instructions receives the data from the former instruction using data forwarding, right? So in this case, so we can just check the RS1 and RS2 in EX stage because the data forwarding is performed in the EX stage, and we can just check the RD in the different stages. Okay, so this is the condition, the basic condition of the data forwarding. Okay, let's see the condition of data forwarding. So as I mentioned, we can just check the RS1. Okay, RS1 and RS2 of the in the EX stage. So you can find that the representation is a little bit different, right? So you can find the ID/EX. So what does that mean? This is the pipeline register. The pipeline register between ID and EX stages, right? So this is the pipeline register. And then you can find the dot register RS1. So this means the output, the output port of this pipeline register. So what does that mean? So this is, as I mentioned, the pipeline register is the D flip-flop, okay? And then the flip-flop has the D input and Q output. So if this pipeline register is the ID underbar EX pipeline register, then this is this Q. If this is the RS1, then it becomes the ID/EX dot RS1. Now what is this RS1 signal? So actually, so in the pipeline register, okay, so where is the pipeline? So you can find the ID and EX, and then this is the output of this pipeline register. So this is the signal in the EX stage. Okay, so this is equivalent to the RS1 in EX stage. That's my representation, right? So the AL operand register number in EX stage, okay, in the EX stage are given by ID/EX dot register RS1 and ID/EX dot RS2. So this is the RS1 and RS2 in EX stage, right? So you can find the, so these are RS1 and RS1, RS2 in EX stage. And then we need to check the, what is this one? RD. Okay. What is this RD? So you can find the EX/memory. So what is this RD? This is the RD in memory stage, right? And then what is this RD? So you can find that this is the memory/write back. So what is this RD? This is the RD in write back stage. Okay, so as I mentioned, we can just check the equality of the RS1 or RS2 in EX stage with the RD in memory stage or RD in write back stage. So if this condition is true, right, then we can perform data forwarding from this one. So it means we can forward the RD data. Okay, so data of the ALU to the input of ALU in the EX stage. Okay, so let's see this one. So you can find the multiplexer here. Okay, and then so this multiplexer is the 3-to-1 multiplexer. So which means that this multiplexer has 3 inputs and then 1 output. So we can select the output from these 3 inputs. And then you can find that the one of input is from the ID underbar EX. So what does that mean? So this is the RS. So this is the data in the EX stage. So it's a normal data. But you can find that, so this is the result of ALU, right? So this is the result of ALU. And then the result of ALU is propagated to the next stage. So this is the memory stage. So and then this is the output of EX slash memory high prime register. So what is this one? So this is the ALU result in memory stage, right? So this can be connected to this input port, right? Also, you can find that the result of data memory and then the result of the ALU is multiplexed here. And then, so this is the actually the final result in write back, okay? And then this can be forwarded to this port, right? Right? So we, we, we check the RS1 and RS2 in EX stage, and then we check the equality of this RS1, RS2 with the RSRD in memory stage. So in this case, we just check the equality of RD in memory stage, so which means the result needs to be forwarded from the memory stage, right? So which means this is the output of this EX and memory high prime register. So this is the result in memory. And then if this condition is met, the RD in write back is equal to the RS1 and RS2 in EX, which means we need to forward the data in write back. So what is this result? This result is here. This is the data which will be written back to the register file. So this is the data in write back. So you can find that this multiplexer received so this is a normal case. There's no data forwarding. This is the forwarding from the so this is the normal. This is the forwarding from write back, and then this is the forwarding from memory. Okay. And then the forwarding unit generate the selection signal of this multiplexer. So which means that the multiplexer can select the output from these three input values, input data. Okay, and then this is for the first input port of the ALU, and we can also apply the same forwarding multiplexer for the second input of ALU, right? So you can find the forward B. So and then the forwarding unit just to check the equality of RS1 and RS2, right? So you can find that RS1 and RS2 in EX stage, right? Because the forward data is required when the target instruction is in the EX stage. And then for the RD data, the forwarding unit received one of RD from this one. So what is this RD? This is the RD in memory stage. And then what is this RD? This is the RD in write back stage. Okay. Then we can just check the equality. Okay. Okay. But we need to also check the some another check the more conditions. Okay. So firstly, the folding needs to be performed if the regular write is 1. So what does that mean? The data folding is necessary when the former instruction store data to the register file, right? So which means that the former instruction needs to write the result to the register file. So in this case, we may require data folding. Okay. So if the data is not written back to the register file, then we don't need to perform data folding. Actually, we need to avoid the data folding. So we need to check the regular write signal. Okay. So if the regular write signal is 1, so which means the result will be written back to the register file. So in this case, we need to check the data folding. Okay. And then if the RD is X0, which means actually, so this data will not be written back. So it is because if the RD is 0, RD is X0, which means that if a certain data, so even though non-zero data is written back to the register file, this non-zero data is not updated. Right. So in this case, we need to avoid the data folding. So for example, so add x0, x0, 1, and then sub x1, x0, and x0 and x5, for example. So actually, the ALU will generate the 1 but as the result of this add instruction, and then because this instruction is the add instruction, then regular write is 1, but the target register is x0. So and then you can find that the sub instruction also read the x0. So this means we can find the data dependency. But if we just put the 1 to this x0, then sub instruction will generate the incorrect result. Okay, so we need to avoid this case. Do you understand? Okay, so if the destination register is x0, then we need to avoid the data folding. So we need to check this one. Do you understand? So this is the condition of the data folding unit. So we can find that the source, so source is the IDX, and then so this means the EX stage, the EX mem. So what does mean? What does this one? This means the data in memory stage, and this is what? This is the data in write back stage. And then this is normal case, it's a no folding. So if the 0, 0, then this is the no folding. And then 1, 0, then it means it's a folding from memory stage. And then 0, 1, this means the folding from write back. Okay. Okay. So based on the these condition, then we can generate the selection signal of the boarding multiplexers. And then we need to also consider the double data hazard. So what is the double data hazard? So you can see this example. So you can find the data dependency between the first the add 1 to the add 2, right? Also you can find the data dependency between the add 2 and add 3, right? So actually if we just apply the data forwarding condition we investigated, then you can just find that, oh, data forwarding is possible between the first add and the second add. Also, data forwarding is possible between the first add and third add. Right. So this is the data forwarding from memory, and then this is the data forwarding from write back. Right. The two conditions, actually the two conditions meet the data forwarding condition. Okay. Then what do we need to select for this add instruction? Obviously, this add instruction needs to receive data from the second add. And this is because this x1 is the latest value. And then, so the following instructions needs to receive the latest value from the register file, obviously, right? So we need to use, so if the data forwarding from memory or data forwarding write back are both possible, so which means that the conditions are both met, then we need to select this forwarding. So the forwarding from, actually, the forwarding from, okay, the forwarding from second to the third add. So we need to select this one. Okay. I want to use the most recent value. Okay. So for this is the final condition. The final condition of the data hazard. Okay, like the port 01. So you can find that the port 01 is activated is a port from the write back, right? But this port from the write back is enabled if the port from the memory is not activated. Okay, so this condition needs to be inserted. Okay, so then, so so it means that there is a priority. Okay, if the data from memory or data from write back are both possible, so we need, in this case, we need to select the data forwarding from memory because this is the latest value. Okay. Okay, so this is some final implementation of the data forwarding, right? So you can find the forwarding unit here, and forwarding unit received the RS1 and RS2 in EX stage, and then it received the RD in the RD in the memory stage, and then RD in the write back stage. Also, the forwarding unit needs to receive the mem write signal. Okay. No. Reg write signal. Reg write signal. Okay. Then the folding unit can generate the folding selection signal for these folding multiplexers. Okay. So I will stop here. So I just explained how to implement the data folding unit. So and then also I explained how to implement data folding in the pipeline architecture, right? So I hope everyone can understand this actually. So pipelining is very simple concept, okay? And then so actually the implementation it can be simple, but actually in order to support the data folding and then some the hazard control, the pipeline architecture is a little bit tricky, okay? Can be a little bit tricky, okay? But you need to understand. Okay? This is the very important part of this course, okay? So I'll stop here. Then I hope everyone can watch this video before the next class, okay? So see you in the next class.